Hello, class. Up to this point, we have been doing Aldol reactions with one reagent, where we take, let's say, an aldehyde, treat it with sodium hydroxide, and then this reacts with itself to form the product. But now we're going to take a look at something that's called a crossed aldol reaction. And a crossed aldol reaction is where you have two aldehydes or two ketones or an aldehyde and a ketone, but they're not the same. You can see that this and that don't look the same. So what is the product or products going to be? To answer that question, well, it all depends on which alpha proton is deprotonated. Or another way of saying it, which enolate is formed. So there's going to be 4 different types of products here. And so I want to show you those. What if we had the aldehyde right here, and we treat it with some base, and we have an alpha proton here that's going to come in and abstract that to form our enolate, okay, which would look like this, right? And then we would treat that with another molecule that looks just like it, like that. So we can envision these lone pairs coming down, that's coming and attacking like that. And so what would we get here? I'm going to keep this molecule right here, okay, O minus. And then this carbon right here attacked it. So there's that carbon. Then we need to draw another carbon, which is there. And then that carbon has a double bonded O with a hydrogen attached. And then we'll do a proton transfer, which I'm not going to show, and we would protonate that. Just like that. So there's a possibility when we take this reaction mixture, this aldehyde could be formed into this enolate and then react with the same aldehyde. That's a possibility. But you could also see another possibility. What if you took this aldehyde, like so? We would treat it with some base. It would abstract the alpha proton. To form the enolate. And then we would have the enolate there. And then that enolate could react with another of the same aldehyde, like so. So these would come back down. Those would come and attack, like so. Now I'm going to take this molecule and just draw it again, like so. O minus. Okay, and we just got to track our carbons. We are forming this alpha carbon right there is attacking here. So that right there is that carbon. And then it is attached to this carbon, which has a double bonded O. And then it has a hydrogen there, that one and that one. But if we come back to this carbon, which is that carbon, we accounted for this one and the hydrogen, but we still have this methyl group right there that we have to worry about. And that would be right there. Then we would take this molecule and do a proton transfer and protonate that guy right there. And we would get that product. Now you can take these, after I do this, I can take the molecule and, I don't know, clean it up a little bit so I can see it better. I don't know, like when I draw it horizontally, it just clicks a little bit better for me. So let's just do it here. So we have 1, 2, 3, 4 carbons. So just go 2, 3, 4. Let's see. So we have on that carbon, we have an aldehyde. Go there, and there. So what do we have on this carbon right here? OH. Is this molecule and that molecule the same thing? 1, 2, 3, 4. 1, 2, 3, 4. We have a alpha beta hydroxy compound. Alpha beta hydroxy. It all matches up. So you could do the same thing for this guy right here. So I'm trying to just find the longest carbon chain here. 1, 2, 3, 4, 5. 2, 3, 4, 5. So that carbon is there. Then this one, and this carbon has a methyl group coming off of it. And I don't have enough space, but see what I'm drawing right here? That's a methyl, which is that guy. And then we come to this carbon, which shows that we have an alcohol on it. And then we go there and there. Okay. Do you see how this molecule right here, this one and this one right here look different? Okay. So those reactions right there, when they're reacting with themselves, it's just called a Aldol reaction. But now we have different combinations. Now let's take a look at this guy reacting with this guy, and then this guy reacting with this guy. Now, isn't that saying the same thing? Not exactly. So let's clean up this board, and I'm going to show you what I mean by that, okay? Now let's take it, and what if we start with this aldehyde? We treat it with the base, and I'm not going to show the mechanism. I'm just going to go right to the enolate. Like that. There's our hydrogen. And then we take that enolate and we treat it with this species right here. And this one, let's do the mechanism. That comes down, that comes in and attacks like that. So we're going to have 1, 2, 3. 1, 2, 3, just making sure no mistakes are made. And then we have this carbon attacking there. Then we have another carbon right there, which is going to be that. Just like that. And then we do a proton transfer mechanism, which will then do that. Okay? And then we could have the other situation in which we take this aldehyde and turn that into an enolate. Which will give us, not this, will give us that guy. And then that guy is going to react with this one. So those will come back down, those will come there, like that. So I'll just stay consistent here. I'm going to draw this one. And I'm not giving myself the most sport space. Okay. And then attached to that is this alpha carbon. So there's that carbon. And then it has a methyl group attached to it. And then it also has this carbon right here attached to it. Double bonded, like that. Then we do a proton transfer and get that compound. Right. Now, what I recommend that you do is you take these two compounds and the previous two compounds and look at them very carefully, and you'll see that they're all different. So these two reactions right here are a crossed aldol because they're using two different aldehydes. Right? Now, crossed aldol reactions are not very efficient because when you do this reaction right here, what is your product going to be? It's going to be 4 different products. That's not very efficient. Your yields are going to be very, very low. So there are some things that we can do to enhance the yield of crossed aldol reactions. And I'm going to clean up this board and then show you what we can do to increase the yield. So one thing that you can do to increase your yield when you want to do a cross aldol reaction is select a aldehyde with no alpha protons. So that's formaldehyde. There's no alpha protons. And if you take that formaldehyde and treat it with another aldehyde that looks like this, under basic conditions, you're going to get one major product. And we'll talk more about the one major product in a moment, but can you see when you mix this all together, this base cannot abstract this proton or this proton. The only proton that it can abstract is this alpha proton right there to form our enolate. So we would get our enolate like that, and then that enolate would react with the formaldehyde. That'll come back down. And then what would we get? I'm going to redraw that. And then we have this carbon, which is attached to that carbon, which is now going to be that. Back to this carbon, we have a methyl. Then we do a protonation step, and we get that. So if we make that look a little bit nicer, we could have what? There's 1, 2, 3. So we could go 2, 3. And then, so that's that carbon. That carbon, we have a methyl. And then this carbon, we could draw it like that if we'd like. Okay. 1, 2, 3, 1, 2, 3. Yep, just like that. So that's that product. But now, so that right there is the major product. But you might be thinking, whoa, 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 whoa. Why could we not have this get converted into an enolate? Let's make that an enolate. Why could you not just make this enolate and then react it with itself? Yeah, why can this not happen? Well, it can. That will collapse back down. That will come in and attack. And then what would we get? We'd get O minus. And then that carbon, that one, like that, and a methyl. right there. We do a protonation step, convert it to that. So why is this one in blue, the minor product, and this one in pink right here, why is that the major product? Well, it has to go, well, the answer is it's a steric argument. You can see that when this enolate is formed right here, it can attack a formaldehyde a whole lot easier because it only has 2 hydrogens in comparison when you have the enolate attacking this aldehyde that has this ethyl group. So it's just a steric argument. Will you get both products? Yes. But will you have one over the other? Yes. And that would be the major one due to sterics. But this idea of selecting a aldehyde or a compound with no alpha protons will reduce the possible products from 4 down to 2. And more often than not, those 2 products shown here, you can select for one over the other due to a steric argument. So the next, I want to go through another example of a cross-aldol reaction with another formaldehyde, or not, another aldehyde without any alpha protons. Here's another example. Here's benzaldehyde. You can see that here's the alpha carbon, but there's no hydrogens on it. Here's another aldehyde, and it has alpha hydrogens. So the only enolate that's going to be formed is going to be this guy, which we have seen before. That enolate will look like this. And so that enolate is going to then attack this guy right here. So we can bring those electrons back and attack like so. So if I start drawing the product over here, what do we have? We have our benzaldehyde, or our benzene ring, our hydrogen, O minus, and now we have this carbon right there, the alpha carbon. I'm going to draw it right there. Then it's attached to another carbon, that one, which is double bonded. Now, do you see how I'm just elongating these bonds? I'm just getting the connectivity right. And I can draw those bonds as long as I want. And so here's that carbon, and it's attached to a methyl. And then we'll do a proton transfer step to get that guy. So if I clean this up a little bit, we could see something that looks like this. We have an alcohol right there, and then that carbon, like that, and then like that. Okay, so it's cleaned up a little bit. So this molecule in green is the same thing as this one in pink, but for some reason my mind likes looking at it this way. Now when you look at that, that is a product, but it's not you don't isolate this product. Okay? It continues on to the dehydration step. You can't stop it. Remember the dehydration mechanism? You find an alpha proton. You have your base right here. And what's that going to do? It's going to do an E1CB mechanism. And that's going to leave right like that. And so we would get our product that looks like this. Like that. Now, can anyone see, by just looking at this molecule, and answer the question, why can we not isolate this compound? Why does it automatically go to the condensation product? Any ideas? Look at this. It's conjugated. Double, single, double, single, double. This molecule is so stable because it's conjugated. And so that's why it doesn't stop here, because it can gain so much more stability by becoming more conjugated than it is right here. So you can't stop it here. It goes all the way to there. Okay. Okay, so we will continue looking at different ways to do cross-aldol reactions. So I'm going to clean the board and we'll jump to the next topic. Another thing worth noting when you look at aldol reactions and cross-aldol reactions, you could have a situation like this where you treat it with sodium hydroxide. When you treat the aldehyde with hydroxide, it is a reversible process. It's going to generate the enolate just in a reversible fashion. You can also generate this enolate in an irreversible fashion if you use LDA, which is and then that would generate the same enolate but in a irreversible fashion. That's just a little bit of information that you need to be aware of and not be confused if you see it. So the next thing that I want to talk about is intramolecular aldol reactions. Let's clean this up here. So what if we take a look at intramolecular? So intramolecular aldol reactions. Let's see, let's look at an example. How many carbons? 1, 2, 3, 4, 5, 6. 2, 3, 4, 5, 6. So let's say you have a diketone species and you treat that with base. Okay. Now what can happen here? Now this is interesting in the fact that we have alpha and alpha. So which alpha protons do you abstract? Well, it all comes down to the size of the ring that you're going to form. So let's look at the two situations here, or the two possible scenarios. If I abstract this alpha hydrogen off, what would we get? We would get an enolate that looks like this. Make sure I have 6 carbons. 1, 2, 3, 4, 5, 6. You get that enolate. But if you ripped off this alpha hydrogen right there, what type of enolate would you get? You would get like that. Okay. Now take a look at those two enolates. You can clearly see that they're different. Now what's going to happen is an intramolecular reaction. So they're going to react with itself. So what's going to happen is the enolate is now going to come and attack the other carbonyl carbon, like that. So what would the intermediate of this be? Well, the way I do it is I just count the carbons that are involved. There's our alpha carbon, so 1, 2, 3, 4, 5. The alpha carbon is attacking carbon 5, so that gives us a 5-membered ring. So I just go, if I draw this over here, I would just draw a 5-membered ring. That's how I would start. And if I call this carbon 1, then I know carbon 1 has to form a bond with carbon 5. Okay? And then that's 2, 3, and 4. So I see that on carbon 2, those electrons collapse back down. So I have a ketone right there in carbon 2. And then carbon 5 right here would have a alkoxide. But what else is also attached to carbon 5? That methyl group. And then we would have a proton transfer and protonate that to give us that molecule right there. Now, one thing I failed to show you is that we do have heat. Now we have heat. And so we are going to, well, let's not worry about the dehydration right now, okay? Let's just look at this one now. Now what would happen with this one in blue? We would do the same thing. Right? So what's that going to give us here? If I number the carbons, I can number it this way. It's showing, based off the mechanism, carbon 3, 4, and 5. So that's what's reacting. It's that carbon with that carbon. So that's 1, 2, 3. We form a 3-membered ring. And let's draw that out a little bit bigger, shall we? So 3-membered ring, I just draw a triangle. So carbon 3 is forming a bond with carbon 5, and that's carbon 4. So what do we have on carbon 5? We're going to have an alkoxide and that methyl group. We do a proton transfer, and that will turn into an alcohol, right? Can't see that very well, can you? Okay, what's attached to carbon 3? Well, we have carbon 2. That's carbon 2, and then attached to carbon 2 would be a thing like that. Okay. Now, when you do intermolecular aldol reactions, 3-membered rings are too strained. They're not favored. Typically, the intermolecular reactions yield 5- and 6-membered rings. Those are the most probable. So if you have a situation like this where you have 2 alpha protons, you just take a look. Does this alpha proton gives us a 5-membered ring? This alpha proton would give us a 3-membered ring. So we know that we can just totally ignore that one and just worry about this one. Okay. So let's finish this problem out. Now we know that there's heat. So we're not going to have the beta hydroxy compound. We're going to have a condensation reaction. So what would be the correct condensation product? Well, we have to come to here and find our alpha protons. Well, here's an alpha proton, and here's an alpha proton. And we still have base hanging around. So this base is going to abstract the proton that's going to eliminate the alcohol in the E1CB mechanism. So the E1CB mechanism. So it's going to have to choose the proton that is adjacent to the carbon that's attached to the alcohol. So this is going to come in and grab that proton like that. Boom, boom. And that's going to give us our product. 5-membered ring. Boom, boom. Just like that. So there's an example of a intramolecular Aldol condensation reaction. Okay. So we have been looking at aldol reactions, which consist of reacting a aldehyde or a ketone with sodium hydroxide or LDA to form enolates. We can do the same type of reaction, but this time with esters. So ET just is the ethyl group. So we could, if we wanted to, we could replace that ET with an ethyl group if we would like. But so just make sure you understand what that is. But I'm going to stick with the letters for this example. So what we have is a ester. And if we treat it with a base, we can form basically another type of enolate compound, which will then attack itself. So if I can circle this here, do you see how we have 1, 2, carbons 1, 2? So we could say, hey, that's 1, 2. What's going to happen is it's going to react with itself and get us that piece right there. You see, that's carbons 1 and carbons 2. But what does this piece not have anymore with it? It's no longer has the OET with it. So this will make a whole lot more sense when we look at the mechanism. Where are all these pieces coming from? So to just get started, you can see that there's 2 pieces right there. And those 2 pieces all come from this 1 piece. So when you do these types of reactions where what's happening is when you look at the first part of the mechanism, what do we have here? We have an alpha carbon. And alpha carbon has alpha hydrogens. So this base right here, which I'm just going to represent with a B, what's the first step? That base is going to come and give us something that looks like this. Do you see how that looks so much like a enolate? Okay. And so for our purposes, I am going to call this an enolate, okay? So there's no confusion. So here's our enolate. So that's very similar to the aldol reaction. But what's the difference? Well, when we're using an ester. And when we're using an ester, we call that a Claisen condensation reaction. Okay? So now when we take a look at this Claisen condensation reaction, there's some things that you need to be aware of that are very, very, very important. Okay? And the first thing that we need to be aware of is what is the name of the product that is formed. So let's just redraw it. So the product is going to be, it's going to have a general name. So the general name for this species is a beta keto ester. So what we're doing here so what's on the beta here? A beta keto ester. So so what we have here is this is our alpha. And then where's our beta? So let me pause for a minute because I'm mixing something up here. Let me pause this for a second. Okay, so when we look at this name, the beta is associated with the keto. So that's implying that there's a ketone present in the molecule. And you can see the way that I labeled these carbons. There's our alpha, and then this is our beta. So the keto or the ketone is going to be on the beta carbon. And then we have a ester, which is right there. So the functional group that we generate when we do a Claisen condensation reaction is we form a beta keto ester. So that's the first thing that we need to be aware of. The second thing that you need to be aware of, and this is a very, very important rule, is that on the alpha carbon of the starting material, you have to have 2 hydrogens. You have to have at least 2. In this reaction, we have 3, so we're good to go. But if you only have 1 hydrogen, it does not work. And you're going to see why it doesn't work in the mechanism. The next very important thing to notice is that the base that you choose to use to form the enolate, that base right here has to match that part of the ester. It has to match perfectly. Because if you chose to form the enolate using hydroxide, what happens when you take hydroxide and treat it with an ester? You hydrolyze the ester. If you choose hydroxide as your base, you will take this guy and convert it into a carboxylic acid. You don't want that to happen. So you need to use this, and that has to match. That's the other rule that you need to be aware of with Claisen condensation reactions. All right. And then the next step, or the next thing you need to remember, is mild acidic workup. And the reason why you have to use mild, because if you use a more stronger acid, let's say if you want to, let's say if you form the hydronium, okay, and you use a stronger acid, what happens when you take esters and treat it with acid? You're going to hydrolyze this and turn it into a carboxylic acid. We want the ester. You don't want to turn that into a carboxylic acid. So what you have to do is use a very mild acidic workup. And the one that chemists typically use, very mild, would be ammonium chloride. Just add a little bit of that salt into some water, and you can do a mild acidic workup to get our product. So I've talked about all the rules here, but now let's look at it mechanistically so we can see how all these rules play into it. Okay? So let's start down below. Just give myself a little bit more room here. So we have our alpha protons, so we have the ethoxide that's going to come in and deprotonate and form our enolate. And these are reversible. So what do we have here? we've generated our enolate, like so. And now it's just going to react with itself. So mechanistically, that's going to collapse back down. That's going to come in and do that. Now, let's just keep it consistent here. So I'm going to take this molecule and just redraw it. O minus. And there's the alpha carbon. And there it is. Then it's attached to another guy, that carbon, and that is attached to the O ethyl. Just like that. Okay, now we're under basic conditions. Now what's interesting now is this tetrahedral intermediate here. We're under acidic, or we're under basic conditions, so we're not going to protonate this. Okay. Do you see with the product that I have now? I have two O ethyls or ethoxide groups, but in our product I only have one. So one of these guys is going to be kicked off. So which one do you think it's going to be? Well, it's going to be the one that has this negative charge on that oxygen, because there's our tetrahedral intermediate, and this guy can collapse back down and kick that guy off. So let's linearize this a little bit and make, so there's what? 1, 2, 3, 4 carbons. 2, 3, 4. We have the OET. And then we have a double bond right there. But what else did we generate? We kicked off that guy. That's negatively charged. Okay. So there's our beta keto ester. But we generated that base right here. And we're under basic conditions, and now we have an alpha proton that's more acidic than at the starting, because it's sandwiched between two carbonyls. So we have a hydrogen right here that's really acidic, and you can't stop this base from reacting with it. Okay. So it's going to grab that proton and it's going to break that bond and put the electrons there. Like that. Now, paying attention, every step here has been reversible, right? So this would be reversible as well right there. But look at when we get to this point right here, it's really just driving it. So because this proton is very acidic, we're in basic conditions, and this intermediate, or this species right here, is very stable. All right. Why do you think it's very, very stable? Double, single, double. It's conjugated. So it's a very stable, and because it's so stable and you can't stop it, the reaction is driven to completion. And that's where the reaction stops. Now you add step 2. Step 2 comes in, ammonium chloride. That's going to be an acid source, so I'm just going to represent it by an H+. And what happens is we do a proton transfer. That collapses down. This comes and grabs the proton to yield our product. And our product, you can't really see it very well, so let's redraw it. So our product would be 1, 2, 3, 4. Like that. So that's our beta keto ester. Now what I want to show you is highlighting the importance of why you have to have at least 2 alpha protons in your starting material. So what I want to do is take this whole mechanism and just add some carbons and highlight why that is such an important rule. So what if I put in 2 more carbons right there, and now we only have 1 alpha hydrogen. Now, if we did that, we would predict our product to look like this. But that reaction right here at top now, when I've added those 4 carbons there, does not happen. Let me say that again. This reaction does not occur because we're breaking one of the rules. It does not have 2 hydrogens. Now let's go through the mechanism and see why that's the case. So we have to be very careful here and making sure we get our 2 carbons added. So we have our carbon and a carbon there. Okay. So what type of enolate is that going to form? So the mechanism is fine. It's going to form, our 2 carbons are right there. So that's the enolate that we've now made. Okay. And so let's put on our 2 carbons right there. So this would happen. Beautiful. Make sure we have our 2 carbons there. Okay. And then we have that carbon right there is that carbon. So that carbon has to have 2 carbons there as well. Okay. So we can envision this process happening, kicking off the ethoxide to getting us here. Now this intermediate is going to look a little different because we have a carbon and a carbon that we have to add, and then there is a carbon and a carbon. Now we're in a situation where there's no hydrogens to be abstracted. The reason why this reaction works is because of this step. This step is basically irreversible. It's not completely, but it is so strong in the forward direction that it drives the reaction. And when you don't have a alpha proton here to be deprotonated to drive the reaction to this stable intermediate, it doesn't go. So you have to have 2 hydrogens at least, because we abstract one of them and we need a second one at this step of the mechanism to drive it to completion. And if there's no hydrogen, it does not go. So that's the reason why those rules are so important. Let's see here. Okay. Let's see, what time do we have? 49 minutes. So in the next video, we will talk about, just like when we looked at aldol reaction, we had crossed aldol reactions. Well, we can have the same thing with Claisen condensations. We can have crossed Claisen. And then we can also have intramolecular Claisen condensation reactions. And when you have an intramolecular Claisen condensation reaction, we call that a Deichmann reaction. So I hope you're seeing that when we're dealing with esters, they behave very similarly to aldehydes and ketones. So the mechanisms that we've been going through should be very familiar, and that will help you in your studying. Okay, so that's where we'll stop for now.